an algebraic, then if I is both proper and modular, then its closure is also proper. So recall that modular ideals means that there's some u in A such that for every A in A minus UA and A minus AU are both in the ideal. So in particular, if A is unital, then every ideal is modular, and that's useful because of the following. If I is a maximal modular ideal, then I has to be closed. So in particular, again, if we're in the unital situation, maximal ideals are always closed ideals. Okay. And then we have the following little result, which is not so difficult to see. If we have a commutative Banach algebra, so recall that if we have a modular ideal, then the quotient itself is unital. So if I is maximal, then this quotient is going to be the complex numbers. Okay. So we're nearly finished up with Banach algebras and can move on to C-star algebras, but just, oh no, that's a lie. We have a little bit more to do. Okay, but anyway, we need to know what we mean by a homomorphism in this case. Thanks. So between Banach algebras, we mean a algebra homomorphism which is continuous. So not a very surprising definition. And if A and B happen to be unital, then we have the notion of the unital homomorphism, which will just map the unit to the unit. Okay. And if we have a homomorphism, we can also talk about its norm. And that is the soup of the norm in B of phi A, where A has a norm at most 1. Okay, so continuous homomorphisms behave how you would want them to. In the world of Banach algebras in particular, we get that the kernel of a homomorphism is an ideal. And remember, when I say just ideal and don't put any extra descriptors there, I mean a closed two-sided ideal. So that's what we get for the kernel of a homomorphism, and that's not so hard to check. So I should say that this homomorphism is from A to B. So it's an ideal in A. Okay, so recall last time we learned about the unitization of a non-unital Banach algebra. And of course, we get a homomorphism that's injective of A into A tilde. Remember that this as a vector space is just A plus the complex numbers. So this is just sending A to A0. This is evidently an injection. So we just identify A as a subalgebra of A tilde. So normally I won't write it in this form. I'll just write it as A. I think I said that last time. And in fact, we get that it's an ideal in A. So A is always an ideal in its unitization. And that's not so hard to prove. You just show that this projection is a homomorphism, and then the kernel is going to be A. Okay, so that finishes off our short blurb on ideals. And now we will talk about the character space of the Banach algebra. Okay, so if we have a Banach algebra A, character on A is a non-zero homomorphism from A into the complex numbers. And we will denote by omega A the set of all such characters and this is called the character space of A or the spectrum of A. And we'll see why it's called the spectrum, which is probably a better name for it in a moment. So this is a pretty important object, especially when we're looking at commutative things. So we now have something that is both unital and commutative. That's important here. Then if we evaluate a character on a point on an element A in our Banach algebra, then we actually get something that's in the spectrum. A character will always have norm 1, and here's how we relate to the previous section. First of all, the character space is always non-empty. And if A is not just the complex numbers, then we can identify tau with its kernel. And this is a bijection between the character space and the maximal ideals of A. So the character space in this commutative setting gives us quite a lot of information already about the Banach algebra itself. So let's prove this. How A is in the spectrum of A. Suppose otherwise. Then recall that this is the set of elements such that 1 minus lambda is not invertible. So that means then that this is invertible. And let's just call it inverse B. Okay, so that means that the definition of the inverse. And now we want to apply the character to this. So it's an algebra map, algebra homomorphism, which means if we apply tau at 1, we get 1. And again, it's a homomorphism, so we just get tau of B and then tau of this thing. Again, it's going to be an algebra homomorphism, so expanding this out, we just get, but of course, this here is 0. And 1 can't be equal to 0, so that's a contradiction. So we've proved 1. Okay, now we want to show that the norm of tau is 1. Recall that the norm is the supremum of the norm in, now it's going to be C, of all elements with norm most and most 1. Okay, so let A be an element of A with norm at most 1. Well, we know that tau A is in the spectrum. And we know that the spectrum is contained in the ball of radius norm A. So we get that tau A is at most 1. And then, of course, we already observed that tau 1 is equal to 1. So this supremum is obtained, which gives us the result there. So we still have to prove 3, which is that the spectrum is non-empty. And when A is not the complex numbers, we have this bijection between the character space and the maximal ideals. Okay. So let's first suppose that A contains a proper ideal. Which we'll call I. Then, since we are in the unital case, I is contained in a maximal ideal. These always exist in the unital case. Contained. And by what I actually just erased, that was sort of stupid of me. We know that since this is a maximal ideal and A is unital and commutative, quotient is equal isomorphic to the complex numbers. And so this quotient map is a character. Otherwise, if A contains no proper ideals, then for any non-zero element A, we can look at the ideal generated by this guy and it will be everything. So what does that look like? It's commutative. So it looks like the set of all elements in A times this little a. Of course, you can put it on either side. It doesn't matter because it's commutative. And then we want to take the closure. And this has got to be all of A. So in particular, there exists some element B in A such that B is, so we don't know for sure that we can multiply B to A and get 1 on the nose, but we can at least get close. We can certainly get within 1. And then we saw that whenever we have this norm bounded by 1, AB is invertible. And since AB is invertible and everything is commutative, you see that A itself has to be invertible. Okay, so what have we shown here? Every non-zero element in our commutative, unital commutative C-star algebra is invertible. So we saw last time that that means that A has to be isomorphic to C. And this isomorphism is a character. So whether or not A contains an ideal, we have shown that the character space is always non-empty. Okay, so now the second part, we need to show that we have this bijection between characters and maximal ideals. And this will only happen when A is not C, so assume that's the case. Okay, so if J is a maximal ideal, then as we saw a moment ago, this quotient map is character. And of course, J is the kernel. So that gives us one direction. Now we want to see that if we have a character, then its kernel must be maximal. Okay, we already know that since it's a Banach algebra homomorphism, this is at least going to be a closed ideal. And again, since we're in the unital setting, we know that this has to be contained in a maximal ideal. So J is maximal, so we get that the complex numbers are isomorphic to this quotient, and the kernel tau is contained in J, so we get that this is contained in A mod the kernel of tau, but that has got to be C. Therefore, in fact, this maximal ideal is exactly the kernel of this character. Okay, so I can't tell if there are questions in the chat because I only see my giant face. It's kind of disturbing actually, but okay, I trust somebody is watching. Okay, right. Erase some chalkboards here. Actually, let me come back to what we have here. So we have that the norm of tau is equal to 1. And of course, since this is an algebra homomorphism in particular, it's a linear map into the complex numbers, which is continuous. So this is telling us that actually the character space is contained in the unit ball of the dual. So we can equip omega A with the weak star topology coming from the dual. And let's do that. So this is now a nice topological space. So remember that this is basically the topology of pointwise convergence. You can think of it that way. Okay. So again, unital and commutative. Actually, do we even need commutative? Yeah, we do for this theorem. Okay, so in the last theorem, we saw that tau of A is always contained in the spectrum of A. And this tells us, in fact, that is the entire spectrum of A. Okay, so we saw the one direction that this is contained in here. So let's show the other direction. Suppose we have some lambda in the spectrum of A. Then by definition, we know that A minus lambda 1A is not invertible. So what does that tell us? The ideal generated by A minus lambda is a proper ideal. And as the usual trick that we've seen so far, that means it's contained in a maximal ideal. Which has to be the kernel of a character. So we get that 0. And this is, of course, just 1. So we see that indeed lambda is equal to tau A for this character. Okay, and then just a little corollary. So this has been for unital commutative Banach algebras. We can also say something about, briefly about the non-unital case. So A is non-unital, still commutative. Then for any A in A, we have something similar to the previous result, but now we have to also include 0. So remember, right at the end of the last lecture, we defined what this meant for a non-unital Banach algebra. You have to look in the unitization, and just leave that as a bit of an exercise. It shouldn't be too difficult based on the last theorem. Okay, so as I noted before, we want to equip this character space with the weak star topology. So we might ask, what kind of topological space do we get? And it turns out we get a very nice locally compact Hausdorff space. And in fact, when A is unital, it's going to be compact. Okay, and I guess I sort of already mentioned why this would be. We saw that this is going to be a weak star closed subset of the unit ball of the dual. And so that this is compact now just follows from the Banach Algebras theorem. So that implies that compact Hausdorff, sorry. Thus, omega A itself is locally compact. Should not be a minus, but that should be a union presumably. And when A is unital, we don't have this part. So omega A itself is closed and hence compact. Okay. So now we will finish off our, we will move on to C-star algebras very, very shortly. We will just end with so-called Gelfand representation theorem, which will tell us that we can always map a unital commutative Banach algebra into an algebra of continuous functions on some compact Hausdorff space. Okay, so I will just define these maps. So for any A and A is a Banach algebra as usual. Define A hat from A to C. Sorry, from if we want commutative. Sorry. So we will just define this to be a hat of tau as tau of A. So these are functions you'll recognize from the usual dual space. And by definition of the weak star topology, these guys are always continuous. So indeed, we get that A hat is in the continuous functions of omega A. This means vanishing at infinity. So they have to be, for every epsilon less than, for every epsilon, there has to be a compact subset of this such that A hat is less than epsilon off that compact subset. But okay, if you're not so happy with that, I'll say more about it a bit later. Just think of the unital setting, and then this is just continuous functions. Map alpha, sorry, A to A hat is called the Galfand transform. And we call A hat the Galfand transform of A. Okay, so now we have the following theorem, which is actually relatively straightforward based on what we've seen so far. So let A be a commutative Banach algebra. Non-empty character space. Then the map from A to continuous functions on the character space, mapping A to A hat, is a norm decreasing algebra homomorphism. So in particular, it's a Banach algebra homomorphism. And the norm of A hat is actually just the spectral radius of A. Moreover, if A is unital, then for every A and A, the spectrum of A is the image of A hat. And if A is not a unital, then the spectrum of A is the image of A hat together with 0. Okay, so have I erased all of this stuff? Okay, so we know that the spectrum of an element A is exactly tau A. So that tells us that indeed the spectral radius is going to be the norm of A hat. And we already observed earlier that the spectral radius is always bounded by A. So this implies that indeed this map is norm decreasing. And it's easy to check that it's also a algebra homomorphism. And that this is true, that the spectrum of A is just the image of A hat, is exactly the theorem we saw earlier. And again, the non-unital was a corollary. So that is that. How am I doing for time? Pretty good. Okay, so far this only says something about the commutative Banach algebras, but we can use this to say something useful about any old Banach algebra. So take an element A and A, and we can consider the Banach subalgebra generated by A and the unit. Okay, then B is commutative. And A hat omega B to the spectrum of A, which is of course just A hat tau plus tau of A. This is actually a homeomorphism. Okay, so this is not so difficult to show. So first of all, that B is commutative. Well, it's going to be just the closure of polynomials in A. So those are clearly commutative. So B itself will be commutative. We already noted that A hat is continuous. And by the, it's continuous. And we know that it's moreover a bijection from the last theorem. So it's a continuous bijection and hence a homeomorphism. Okay, now we finally can move on to C-star algebras, which are of course the main topic of these lecture series. So what is a C-star algebra? Well, it's a type of star algebra. So what do I mean by a star algebra? This is an algebra A. together with an involution or star map. So this is an order 2 anti-homomorphism. In other words, we want it to satisfy the following. If I take a star twice, I get back what I started with. And it's an anti-homomorphism. So if I take the star of A times B, I get B star A star. So when we have a star algebra, we have a bunch of special elements. So I'll just give you a bunch of, it should really be definitions because there will be more than one all at once. So take a star algebra A. So for an element A and A, we call A star the adjoint of A. If it so happens that A is equal to A star, we say A is self-adjoint. If we have some element P in A such that P is self-adjoint and also an idempotent, then we call P a projection. If we have an element A and A that commutes with its adjoint, legible? Yeah, I guess so. Then we say that A is normal. And if it commutes with its adjoint, so U is normal, and also its adjoint happens to be its inverse. So this is assuming A is unital. I should say that if A is unital, the rest need A to be unital. And U satisfies U star U is U star is 1A. Then we call U unitary. And notation, I will denote by A subscript SA, all those elements in A which are self-adjoint. And I will denote by curly U A all those elements in A which are unitary. And again, that requires, of course, that A itself is unital, or that doesn't really make sense. Okay, so that's a star algebra. Now, a Banach star algebra is the obvious thing. It's going to be a algebra that is both a star algebra and a Banach algebra. And we'll need some compatibility condition between the norm and the involution. Going to be a Banach algebra A, which is also a star algebra. And we need it to satisfy the norm of the adjoint of an element is the same as the norm of A. Okay, so this is a Banach algebra, so it's submultiplicative. You'll note that we always have that this is A star A will always be at most the norm of A squared. And when we have an equality, this is exactly when we have a C star algebra. So this might seem like a slightly mild addition, but it turns out to make C star algebras quite well behaved. So this is the definition of an abstract C star algebra. So this should be a complete normed star algebra. And we want it to have submultiplicative norm. Satisfying what is called the C star equality. And what is that? It's exactly this with an equality. And any norm which satisfies this, we'll call that a C star norm. Okay, so again, it seems like maybe there isn't so much of a difference between a Banach star algebra and a C star algebra. In particular, it's clear that an abstract C star algebra is going to be a Banach star algebra, but these are indeed Banach star algebras are more general than abstract C star algebras. And here is an example. Really more of a non-example of a C star algebra. It's going to be a Banach algebra, Banach star algebra that's not a C star algebra. Okay, so little L1 Z will be a set of sequences indexed by Z. Such that summing over the absolute value of the xn is finite. And we can give this a norm, which will be just exactly this sum here, which is of course finite by definition. Call this the one norm. And we can give this some operations. So addition will just be coordinate-wise, and we want multiplication to be convolution. So if we have two elements, x and y, the nth entry is going to be xj times yn minus j, where we sum over all such j's. And we can put involution by defining x star at n. This will be complex conjugate of not n, but minus n. And you can check that this indeed gives us a Banach star algebra. But this will not be a C star norm. One norm is not a C star norm. So for example, take x in L1 Z to be x0 is 1, x1, x2 is -1, and xn is 0 for all other n. Then what is x star x? Well, we need to do this convolution product. X star j, xn minus j. X star is just complex conjugate. All of these are real, so we don't need that. And we just get minus j, xn minus j. So obviously, most of these terms are 0. The only ones you get that are non-zero are -2, -2. And we get some non-zero terms here. So we get x2 is 1, x2 this should be 4. Okay, that's 0, so that doesn't matter. The only ones we get are, did I write this down correctly? Yes. X2, x0, okay. Which is -1. For -1, we also get x1, x0, and x2, x1. So that is 1 1 plus 1. No, sorry, -1 plus 1, which is 0. X0 plus x1 plus x2, x2, which is going to be 3. And then we get, 1, x2, that is again going to be 0. And then finally we get x0 is 2, which is -1. So that means that the norm of x star x, well, we just want to sum up everything's absolute value. So we get 1 plus 0 plus 3 plus 1 is 5. But then it's easy to check that. So what is the norm of x? Well, it's just going to be 1 plus 1 plus 1 is 3. 3 squared, that's 9. So this is not a C-star norm. Okay, as usual, we want some notion of a structure preserving map between C-star algebras. So what is that in this context? So take two abstract C-star algebras. A star homomorphism. Phi A to B is an algebra homomorphism which also preserves the star. We want that phi of A star is mapped to phi of A star, where the star now is in B. And once again, if A and B happen to be unital, then we have the notion of a unital star homomorphism. So that's just going to be a star homomorphism mapping the unit to the unit. Okay, so this seems like a reasonably obvious definition, but one thing you'll notice is that I have not asked that phi is continuous, which we did when we had Banach algebra morphism. Right, but it turns out that C-star algebras are so nice that this definition will guarantee that these guys are always continuous, and we'll see that in a little while. Yeah, so Spillin wrote in the comment, I didn't see it in time, sorry about that. Yeah, it does require closure as well. So with respect to the homeomorphism, I guess I didn't say that, sorry about that. Okay, so unless otherwise specified again, by an ideal in a C-star algebra, needs a closed two-sided self-adjoint ideal. And following definition, A is simple if it has no non-trivial ideals. Yeah. If it's two-sided, yes, I guess it does. Yeah, yeah. Yeah, that's a good point. Okie dokie. So I don't know if people heard that, but Tristan just pointed out that actually the closure will imply this self-adjoint when it's a two-sided ideal. So that's sort of superfluous information, but we didn't prove that yet. So that is why I mentioned it. Okay, so we had a non-example. Let's see some examples. So the first one is something we all know and love, the matrices. So take some non-zero natural number, and I will denote by just Mn, since we're always working over C. This is actually MNC, but often in the literature you won't see the C. So this is what that means, and this is just, of course, the n by n matrices with complex entries. And we can equip this with its usual operations. So it's just matrix addition and matrix multiplication. And the star will just take a matrix A to its adjoint. And we need a norm. The norm will just be the operator norm, which we've seen a few times now. So take your matrix A and look at AX for X and Cn with norm at most 1. So this is just the usual norm in C to the n. And this makes Mn into a C-star algebra. And in fact, it's going to be a simple unital C-star algebra. More generally, we don't need to, of course, restrict ourselves to C to the n. We can always look at the bounded operators on any Hilbert space. And we use exactly the same operations. So adding two operators together or composing the operators for multiplication. And of course, the star takes your bounded operator to its adjoint. And again, the operator norm is defined completely analogously, but now this is of course in H, not C to the n. This is the C-star algebra. Again, but it will only be simple when H is finite dimensional. So when H is not finite dimensional, it has ideals. And here's an example of one, which is again a C-star algebra. And that is the compact operators. Then K of H is a C-star algebra with its inherited operations. So the only, I suppose, non-obvious things are that this is first of all closed, and second of all closed under taking its adjoints, but presumably you've all seen that before. And this is going to be a non-unital. Well, only if H is infinite, I guess, but okay. Non-unital whenever H is infinite dimensional. So it's a nice example of a non-unital C-star algebra. And more generally, if we have any closed subalgebra of D of H, that's closed under taking the adjoint as well, then this will be a C-star algebra. And we call such a C-star algebra a concrete C-star algebra. And we will see later on that concrete and abstract C-star algebras turn out to be up to star isomorphism, the same thing. Okay. So another very important example that we will see quite frequently and is always something useful to have in your head when you're deciding what should or should not work for C-star algebras are the commutative C-star algebras. So, for example, let X be a locally compact Hausdorff space. So I have been implicitly using this before, but now I'll define it a little bit better. We say that a function f from x into the complex numbers vanishes at infinity if for every epsilon greater than 0, we can find a compact subset such that the set, such that f of x is less than epsilon for every x outside of K. So if you think of some nice locally compact Hausdorff space, like a half-open interval, this is just telling you that your function has to be zero at zero, essentially, or approach zero as it goes to zero. So C0 of x is those continuous functions vanishing at infinity. And we equip this with pointwise operation. And we define the adjoint of the function to be the complex conjugate. And we need a norm, and that will just be the sup norm. And note that this really does define a norm exactly because we've asked that these vanish at infinity. And otherwise, this wouldn't work. Okay, so it's easy to check that this is going to be a C-star norm. So this is a C-star algebra. And moreover, it's clear that it's commutative. Right, it's commutative, and it's unital precisely when X is compact. And notice that when X is compact, then this vanishing at infinity condition is meaningless. So we just get all the continuous functions. In which case we just denote it by C of X. And in this case, it will be unital. And exactly equal to these functions vanishing at infinity. So we won't normally bother with the zero when X is compact, and that's a good way to remind yourself whether we're assuming compactness or not. Okay, let's see some not so difficult properties that we get immediately just by virtue of having a C-star norm. So or perhaps I could call this why C-star algebras are much nicer than general Banach star algebras. So recall that when we had a Banach algebra, then we insisted that the norm be normalized at 1. Well, thanks to the C-star equality, this is automatic for a unital C-star algebra. And more generally, if we have a non-zero projection, or if A is unital and U is a unitary, then the C-star equality implies that these both have norm equal to 1. So this is the C-star equality. This is the projection. So this is actually P squared, which is again just P. So we see that P is equal to 1. And a similar trick using the unitaries. So we know that this is 1 since it's a unitary, and that has norm 1. So this gives us some nice information already about, for example, what the spectrum of a unitary can be. Oh, I'm about over time. Okay, let me just finish off quickly with what the spectrum of a unitary has to be, and then I will continue next time by showing you that this can tell us what information about the spectrum of a self-adjoint element. Okay, so U in a unitary. So A is a unital C-star algebra. Well, if we have some lambda in the spectrum of U, and we just saw that the norm of U is 1, so that means that by the spectral radius condition, this has to be at most 1. But we also have that U star is equal to U inverse, which is also unitary. And it's straightforward to check that lambda inverse will be in the spectrum U star. So we better have that 1 over lambda is also less than or equal to 1. And so this tells us exactly that the norm of lambda is 1. And so the spectrum of any unitary is contained in the unit circle. And this relatively simple observation will allow us to see in the next lecture that if you have a self-adjoint element, its spectrum has to be real. Okay, so I'll end there and hope to see you guys next week.